Wow, this was a chapter with a lot of detailed descriptions of this library.
Oh yeah, I think like it's just we can just get a flavor of what reinforcement learning is. It's like too much of information to cover in a single chapter.
Yeah, they are going to do a course on it, I think. I don't know if they've chosen a textbook or maybe the lectures that are on YouTube, because David Silver's done on some on UCL. They're on YouTube. But yeah.
Yeah, I am going to follow it when it starts because reinforcement learning is quite interesting to me. And I think they plan to base it on this David Silver's lectures and Sutton's book. It's like a really popular reinforcement learning book. And I've started it some time ago, but then I realized I really either need to spend much more time on it or just to postpone it for now, because it's like it doesn't work this way when you just read a book a bit and that's all. And I went different way. I was like implementing the stuff which was described in the book from scratch, but that was taking really a lot of time, and I had to like focus on some other things. And yeah, but I'm looking forward to like coming back to that, and yeah, quite an interesting area, but. Really, even judging from experience with this chapter, it's really hard to make it work well.
Yeah, and you need a lot of compute as well. There's just so much compute going on. So let me
I just read a quote, I think somewhere in the page, it says the convolutional networks learn or works, and then RL, you need to force them to work.
Oh yeah, you see it there. RL must be forced to work.
Yeah.
Oh, yeah, and this is a major genre, not as widely adopted as regular deep learning. Yeah, I wonder if there's any applications to natural language using reinforcement learning. If there was, I'd be a lot more inclined. But game playing and stuff like that is not really my thing.
So the down below, so the Google uses RL to optimize its data center cost, and it is used in some robotic applications. I think somewhere I read it for the recommender system as well. So down below, yeah, for hyperparameter tuning and in a recommender system. So I guess that recommender system is where perhaps your NLP comes into picture as well.
Yeah, although I'm guessing that's kind of like regression of some sort. But yeah, I might see. Yeah, if there's a paper, I might read it just to see if there's anything applicable to that. Yeah, cool.
Reinforcement learning is like learning problem formulation rather than it's not like it's just another level of like on another level of abstraction compared to like different deep learning techniques, I would say. And you can apply it to any problem if you formulate it like a reinforcement learning problem. What I saw a couple of papers applying reinforcement learning to like text generation and summarization, although I didn't spend really much time reading those. And yeah, for now, it doesn't look very popular because it's hard to make this deep reinforcement learning system work, and also you need really much more compute for that.
Oh, yeah.
But there are some applications I can maybe find
okay,
the
there is.
headings.
Oh yeah, there's an archive on the archive that was in Cerniverse in 2019. Yeah, so okay, yeah, it's only 6 pages long, so yeah, I'll download that and have a little look at it maybe next week. Okay. Oh, damn. Save that. Yeah, getting back to what we were doing. Okay. So deep Q learning. So guys, I'm going to apologize because as I say, I don't fully understand this stuff, but we'll go through it and see what we can get. I don't know if going forward from next week, if it's worth us switching to Thursday and we can watch what those guys have done. What do you guys think about that? Because there might be some people who are a lot more. What I'm trying to say is instead of doing it on a Wednesday, if we do it on a Thursday, we can see what they did on Wednesday morning. I mean, we'll still try and read, but at least, you know, we can have a little chat about it and we can see what they did. What do you guys think? Because there's going to be one session next Wednesday on reinforcement learning, but then there'll be reviews of the chapters, which I think Joseph's doing. And it might be a good idea to see what he's going to say. You know, I mean, we can join them on Sunday, and then on Thursday we could just watch what they did on Wednesday night.
Well,
yeah, that sounds reasonable.
But this is not the last chapter.
There's a little bit more.
Yeah, there is.
Oh, there's the is the production deployment one.
Yeah.
But yeah, I was suggesting that from next week, if we do it on Thursdays, then at least we would be able to see what they're saying, and we can kind of comment on it if we wanted.
So okay, so you mean like just to watch what they have done on the Wednesdays, and then we meet here to have a discussion on what they have said.
We can watch it together. I mean, the idea would be, you know, we'd read it. Okay, so I want you guys' opinion, but what I was thinking was, if we start at the normal time and we read, you know, the section, and then say at 6:45 or 7, we then watch them discussing it, and then we can chime in as well. Because, I mean, I can just download the video and just play it to all of us,
Okay.
and we can have a chat while they're kind of discussing it as well.
Yeah, makes sense, because I think yeah, makes sense. That will help us to understand, as well as I think have a more discussion. Makes sense.
Although it's interesting, Slim is actually doing all of them. Oh wow, that's a lot.
But he's gone. I think somewhere he mentioned Joseph. I think he used to be in the class when it started, but afterwards he kind of like trickled out. So I'm not sure whether he's gonna do this.
Oh, okay. We'll see who's going to do it. As I say, some of these chapters I haven't fully read them, and it's a bit too much to do them within like a week, because they're doing like almost 5 chapters in 1 week, or in one session. So yeah, whoever's going to do it, you know, hopefully they'll put in a bit of effort. But yeah, well, let's try it anyway next Thursday and see how we get along.
Okay. And we're meeting same time?
Yeah, so 6 p.m. hopefully 6 p.m. on Thursday. Unless you guys want to do it later. I mean, I would prefer it to be 7, but then we'll end up going up to 9. Is that going to be a problem for anybody?
Yeah, I think then probably 8 o'clock is dinner time here.
Yeah, okay then. Yeah, we'll do it at the same time. Yeah, cool.
Okay.
Okay, dokie. So getting back to the book. Yes, so now we're now going through a couple of variants of the deep Q learning algorithm. And the first one they say is this fixed Q value target. So it says, in the basic deep Q learning algorithm, the model is used to both make predictions and to set its own targets. This can lead to a situation analogous to a dog chasing its own tail. This feedback loop can make the network unstable. It can diverge, oscillate, freeze, and so on. To solve this problem, in their 2013 paper, the DeepMind researchers used 2 DQNs instead of 1. The first is the online model, which learns at each step and is used to move the agent around. And the other is the target model, used only to define the targets. Okay, so this is a kind of slightly technical problem that they have with this model, with the fact that it's doing two different things, and it's causing it to have all these kind of side effects, kind of dynamical side effects. So they're splitting into two models. But interestingly, what they're doing is they're cloning the main model and then setting the weights and then updating the target, not all the time, but only every n iterations of their loop. So the target is kind of a bit more stable, whereas the other model is changing all the time. So this is kind of what their approach is to get around this problem where of all these kind of issues that they were having with the oscillation and divergence and freezing. So I guess they came up with this empirically. It's interesting as to why it should work. So it says since the target model is updated much less often than the online model, the Q value targets are more stable. The feedback loop we discussed earlier is dampened and its effects are less severe. This approach was one of the DeepMind researchers' main contributions in their 2013 paper, allowing agents to learn to play Atari games from raw pixels. So they've got some hyperparameters as well here they discuss. There's quite a few different hyperparameters, it looks like, that they've they've experimentally arrived at some values. And then it says later in this chapter, we will use the TF agents library to train a DQN agent to play breakout using these hyperparameters. But before we get there, okay, let's look at another DQN variant that managed to beat the state of the art once more. Is that one okay? As I said, it's hard to kind of see exactly where this fits in, but it seems to be that they've what they want is some stability in defining targets, but the other model they want to change in real time. So this is the innovation. I don't know if anybody has any comments on that. Okay, so now another variant of it, which is called double DQN. So in the 2015 paper by DeepMind, the researchers tweaked their DQN algorithm, increasing its performance and somewhat stabilizing training. So again, more stabilization. They called this variant double DQN. The update was based on the observation that the target network is prone to overestimating Q values. Indeed, suppose all actions are equally good, and the Q values estimated by the target model should be identical. But since they're approximations, some may be slightly greater than others by pure chance. The target model will always select the largest Q value, which will be slightly greater than the mean Q value, most likely overestimating the true Q value, a bit like counting the height of the tallest random wave when measuring the depth of a pool. Okay, so to fix this, they propose using the online model instead of the target model when selecting the best actions for the next states, and use the target model only to estimate the Q values for these best actions. Okay, so here is the updated training function. So they've got a training step. They sample the experiences. Next Q values are computed from the model to prediction. Best next actions from those Q values. Some kind of hot encoding. Next best Q values using the target Q values, mask it. Okay, so what they're saying is they don't want to use the target network because it's got this behavior, because it always selects the one with the maximum value. And so that's not purely by chance. That may not be the one that you want. Yeah, I don't quite understand how this is working, but I can kind of see what the problem was, but I don't quite understand how this works in terms of what it's doing in terms of this code. But I've got kind of the idea. I don't know if anybody else has a better idea of what's going on.
Well, I'm not sure about better, but maybe we can discuss it. So as I understand, this target network so it's fixed, right? Every some number of steps, and when we use it every time to choose the actions, it might like be biased towards some overestimated Q values, right?
Yeah.
And they want to avoid that, so they want to avoid choosing actions based on this wrongly estimated Q value. So if we do it without this double DQN feature, we like take some values which might take some actions which happen to have high Q value randomly too often than we would want it. And what they change, so they change it to like we use this network which is updated to select actions, and we use this fixed network only to estimate Q value, like to get the benefit from the previous section, right?
Yeah, yeah. So previously what they were doing was to get the best action and its Q value from the same network. Now they've slightly separated it out, that the best action is gotten from the online model, but the Q value for that action is gotten from the target model. Is that kind of what they're doing?
Yeah, that's how I understand it.
Okay, yeah, that's interesting. Yeah, it's kind of a technical as to why the actions in the online model are not being, I mean, you're still going to select the best action.
Yeah, but an online model, we change, it's affected by the most recent observations. And for this target model, it's fixed for for quite a while, and maybe that causes worse training compared to using those from online model.
Yeah. Yeah, so there's something, okay, so indeed, suppose all actions are equally good. The Q values estimated by the target model should be identical, but since they're approximations, some may be slightly greater than others by pure chance. The target model will always select the largest Q value, which will be slightly greater than the mean Q value, most likely overestimating the true Q value, a bit like weighting. Okay, so it's kind of a slightly technical thing to do with how the Q values are sampled in some way based on the action, I guess. Yeah, okay. Okie dokie. So that was one where the they would how they use the online model and the target model in a slightly different way, and then they've got a third way, which is prioritized experiences replay. So in a sense, instead of sampling experiences uniformly from the replay buffer, why not sample important experiences more frequently? Okay, so this is called importance sampling or prioritized experience replay, and it was introduced in a 2015 paper by DeepMind. More specifically, experiences are considered important if they're likely to lead to fast learning progress. But how can we estimate this? One reasonable approach is to measure the magnitude of the TD error, which is delta is R plus gamma VS prime minus VS. Okay, so I don't know what TD stands for. Does anybody know?
Temporal difference.
Sorry?
Temporal difference.
Okay, and then so there's a delta of an R, and then there's a weighting factor gamma against. So I guess is S the current state and S prime well, is there two previous states in some way, S prime and S and S prime?
It's basically a reward we get for a certain episode, right?
Okay.
So there R is a reward value, gamma is discount factor, and V of S prime and V of S are difference between the expected, like this value, estimated value of state S and state S prime. So we transfer from state S to S prime, right?
Yeah.
And we add this discount between like expected value of the state and a reward, which we get during this episode. So we like rewrite episodes according to the reward it get.
Okay. So it says a large TD error indicates that a transition from S or S prime is very surprising and thus probably worth learning from. When an experience is recorded in the replay buffer, its priority is set to a very large value to ensure that it gets sampled at least once. However, once it is sampled, and every time it is sampled, the TD error delta is computed. And this experience's priority is set to be the absolute value of D plus a small constant to ensure that every experience has a non-zero probability of being sampled. The probability P of sampling an experience with priority P is proportional to P to the power Xc, where Xc is a hyperparameter that controls how greedy we want important sampling to be. When Xc is equal to 0, we just get uniform sampling, and when Xc is equal to 1, we get full-blown importance sampling, because that's the probability. In the paper, the authors used Xc is equal to 0.6, but the optimal value will depend on the task. Okay, so there's another hyperparameter which is controlling how much we want to pay attention to this importance measure, which is the absolute value of this error that they've computed, the temporal, the delta. Is that okay?
Yeah, that makes sense. So this delta shows how much reward plus expected value of the new state differ from what we expected in the state S, right? So if for example, the action lead to great reward and better like good next state than it was expected, the model will be like surprised, and it means that it was a useful experience, right? Or otherwise, for example, if we have a negative reward and we end up in a bad state, and we expect it to be like to have the value of the previous state to be higher. Again, this is surprisingly bad action, and it should be like used more when training. So yeah, that makes sense.
Yeah, so they've got a little caveat here. So there's one catch though. Since the samples will be biased toward important experiences, we must compensate for this bias during training by down-weighting the experiences according to their importance, or else the model would just overfit the important experiences. To be clear, we want important experiences to be sampled more often, but this also means we must give them a lower weight during training. To do this, we define each experience's training weight as W is equal to NP to the minus beta, where N is the number of experiences in the replay buffer. Beta is a hyperparameter that controls how much we want to compensate for the importance sampling bias. 0 means not at all, while 1 means entirely. In the paper, the authors use beta equals 0.4 at the beginning of training, and linearly increasing beta to 1 by the end. Again, the optimal value will depend on the task, but if you increase 1, you will normally want to increase the other as well. Yeah, this is really interesting. It's almost like you need to be an expert in dynamical systems to understand this stuff, because there's so many of these parameters. This is like an engine with all sorts of pistons going in different directions.
It seems like a very empirical thing. This particular, like you see, this beta is set judging from the particular training dynamics, and yeah. Otherwise, it's quite reasonable what they do. I think it's totally makes sense to like you want to see if you imagine some game when most of the actions doesn't really matter, like you don't take important decisions, and the decisions are simple. and you want to learn more from those see more of those situations when you have to take important decisions.
Yeah.
And that's what it does. But you don't want to ruin your training dynamics by only training based on important situations. You also want to have some robust probably behavior in these not very important situations, and that's why I think they introduced this downscaling.
Yeah. Okay, so we move on to one additional one now called the Dueling DQN. So the Dueling DQN algorithm, DDQN, not to be confused with double DQN, although both techniques can be easily combined, was introduced in yet another 2015 paper by DeepMind. To understand how it works, we must first note that the Q value of a state action pair S, A can be expressed as Q of S, A is equal to V of S, where V of S is the value of the state S, and A of S, A, and which is the advantage of taking the action A in state S compared to all other possible actions in that state. So that's the value of Q. Moreover, the value of a state is equal to the Q value of the best action, A star, for that state, since we assume the optimal policy will pick the best action. So the V of S is equal to Q of S A star, which implies that A of S star is equal to 0. Okay, yeah, so if you just fill in the S and A star into this equation, then yes, to get the V of S is equal to QSA star, that must be 0. Yeah. In a dueling DQN, the model estimates both the value of the state and the advantage of each possible action. Since the best action should have an advantage of 0, the model subtracts the maximum predicted advantage from all predicted advantages. Here is a simple dueling DQN model. Okay, so I can't understand what it's saying there, but it's okay. Sorry, guys, can I just reread this? In a dueling DQN, the model estimates both the value of the state, so V of S, and the advantage of each possible action, which is A of S, A. Since the best action should have an advantage of 0, the model subtracts the maximum predicted advantage from all predicted advantages. Here's a simple dueling. Okay, so that's to make the maximum one 0 there. So, okay. So what's happening here? So they've got some input, there's a dense layer, there's another dense layer, there's another dense layer, there's another dense layer. Then you compute advantages, which is the row advantages, minus the maximum row advantage, so that you've got the advantages there now. And now the Q values are the state values plus the advantages, and the model is inputs and the outputs are the Q values. Okay, so this is kind of reweighting the Q values by subtracting the maximum advantage from them by making the state with the highest reward having the highest Q value. Is that kind of right? I don't understand where the dueling is coming from. Is that just because you're subtracting the maximum advantage? That's where the dueling is coming from. I mean, the bit I don't understand is that the Q value would always, the maximum Q value would have still been the same. It's just that you're not returning the advantages, are you? You're only returning the Q values from here. So why reweight the advantages with this maximum, subtracting the maximum from it? Oh, all the Q values will all get changed when they, I guess. The one with the maximum will have its Q value to be the state value. Okay, so that's what you actually want to happen. Yeah, again, I don't have like a good intuition for why this is working. Because if I just look at Q values, then the maximum Q value will always be the same because you're taking away like a kind of like a certain value from all of the advantages. The fact that the Q value for the maximum will be equal to the state values for that is the only effect that this is having. So I don't know quite how that really helps it in a big way. Okay. I don't know if you guys have any comments on that. And then we have the rest of the algorithm is just the same as earlier. Yeah, so this is just a way of getting the Q values. So what have we got here? The rest of the algorithm is the same as the earlier. In fact, you can build a double dueling DQ and combine it with prioritized experience replay. More generally, many reinforcement learning techniques can be combined, as DeepMind demonstrated in the 2017 paper. The paper's authors combined 6 different techniques into an agent called Rainbow, which largely outperformed the state of the art. Unfortunately, implementing all of these techniques, debugging them, fine-tuning them, and of course training the models can require a huge amount of work. So instead of reinventing the wheel, it is often best to reuse scalable and well-tested libraries such as TF agents. Is that okay? So we can just have a little quick look at this library. It seems like it's quite comprehensive, able to do end-to-end, everything you need to be able to train a reinforcing learning model.
Yeah, makes sense.
Yep. Okay, so here now we've got this TF agents library is a reinforcement library based in TensorFlow developed at Google and open sourced in 2018. Just like OpenAI Gym, it provides many off-the-shelf components, including wrappers for all OpenAI Gym environments. Plus, it supports the PY Bullet library for 3D physics simulation, DeepMind's DM control library based on Mujoko's physics engine, and Unity's ML agents library simulating many 3D environments. It also implements many reinforcement learning algorithms, including reinforce, DQin, and DDQin, as well as various RL components such as efficient replay buffers and metrics. It is fast, scalable, easy to use, and customizable. You can create your own environments and neural nets, and you can customize pretty much any component. In this section, we will use TF agents to train an agent to play Breakout, the famous Atari game, using the DQN algorithm. You can easily switch to another algorithm if you prefer. Okay, so I'm not going to go through every section here, but we'll just go through the highlights of it. So installing TF agents, that looks like just using pip. So nothing amazing there. And installing the Atari Gym support from OpenAI is again a pip install. So this is a way of kind of testing that the environment's all working. So it's possible to, it looks like there's a few games, and then Breakout V4, you can just load that environment using the environments from the TF agents.
A quick question. Any idea why does he use this Python -m pip install instead of just calling pip install? What would be the reason for that?
Yeah, that's a good question. I mean, I'm assuming here he's not working in virtual env. If you're not working in virtual env, a lot of the operating systems still have Python 2.7, or at least they did, maybe when he was writing the book, as just Python. So, you'd want to ensure that you were using Python 3 would be one way. But if you've configured your virtual env to be a Python 3 virtual env, then you wouldn't need to do any of this. Interestingly, I don't know why he just didn't use pip3 install. But yeah, I think it's just age. That Python 2.7 was still the rage when the book was written. Python 3 was kind of, although it's been out for a long time, still wasn't widely adopted on the different Aussies as the main default. And this was just a way of forcing it to use Python 3.
Maybe.
It's a guess. I don't know the answer.
Yeah, I was just like curious. Maybe there is some benefit of doing that, but yeah, it doesn't seem that way, right?
Yeah, I can't see any reason. I think this is just the book showing a bit its age. Because as I say, I'm sure he could have gotten the same thing by doing pip3. Probably pip3 is an alias for that.
Yeah.
Okay, so we've got a little bit about how to use the code in TF agents to set up an environment for Breakout 4, for Breakout. Okay, so something about the environment, how to reset the environment, step the environment forward, reward and observation attributes, so what you get from the environment. Okay, so some mechanism for how to step the environment, check whether it's the last step or not, and how to terminate the environment. You can also define the discount factor by setting the discount parameter when loading the environment. Okay. Okay, so, and then we've got environment specifications. Currently, conveniently, TF Agents environments provide the specifications of the observations, actions, and time steps, including shapes, data types, and names, as well as their minimum and maximum values. Okay, so a complete specification of all these kind of core things that you need in reinforcement learning. And he's giving some examples of what the various types of various things are. A way to get at the actual current image. So there's a render for human to get an image back, or to an RGB array to get a NumPy array to see what the current state of the environment is. So there's quite a few functions on the environment in terms of what actions can be taken and so on and so forth. Observations, they're quite large, so we'll downsample them. Yeah. Is that one kind of okay? So this environment's just exploring all the different attributes that are available in the environment, through the environment wrapper. And then we have some pre-processing to make things work with the Atari, I guess, OpenAI, and these are things that you can do to it. So action clip wrapper, clip the actions. There's a discretization because internally the actions are continuous, but you can convert them to discrete. Repeat actions, get the statistics, the time limit, and the video wrapper to record a video of the environment as it's evolving. And to create a wrapped environment, you just call whatever one of these classes and pass it the original environment, and you get a wrapped environment.
So I guess you can apply like number of wrappers sequentially.
Yeah, because each one gives you back an environment. So yes, I would have thought so. Yes. And then they've got this notion of here that you need to give the environment you can't just give it a single episode because that won't have enough data. So they're given here this notion. Okay, that's repeating the action 4 times there, but there is actually okay, so that's a repeating action. And then they've got some additional processing, which is converting it to grayscale, max pooling to get rid of. There's some flicker apparently that can help to get rid of that. Frame skipping, so that you don't play every single frame in the game. And I guess they're using that in combination with the fact that you want to stack 4 frames at a time as input to the model, so that you've got some notion of what's actually happened in time, rather than just giving a single frame where you don't know what the past or the future was, if you're not using an RNN, I guess. And also what happens if you lose your life. Yeah, and then they've got this notion of the wrapper where you stack 4 frames to actually for the model. So this is an environment where, yeah, you do some Atari pre-processing and you stack 4 frames together to generate the output. Is that kind of okay? And then we go on to, so yeah, this is where the stacked bit comes from. So those are the 4. Essentially what they convert them to is multiple channels in the input to the neural network. Each channel is a separate kind of frame, but they've just made it different colors just to show what they are. But obviously it's just data to the model. So, and then we've got a training architecture. So the TF agent's training program is usually split into two parts that run in parallel, as you can see in figure 18, 13. On the left, a driver explores the environment using a collection policy to choose actions, and it collects trajectories, i.e. experiences, sending them to an observer, which saves them to replay buffer. On the right, an agent pulls batches of trajectories from the replay buffer and trains some networks, which the collect policy uses. In short, the left part explores the environment and collects trajectories, while the right part learns and updates the collect policy. Okay, so let's look at the diagram. So you've got the environments, you've got the driver, you've got an observer, you've got a replay buffer, and then training architecture. And then on the training on the right-hand side, you've got a neural network which is generating a policy. Okay, so the driver is generating trajectories for the observer and a collection policy. Okay, I can sort of understand what they're saying, that they've split it into something that just knows quite a bit about the environment and what's possible in the environment, and then something else which uses all the things that are possibly possible and then trains on what it should actually be doing out of all those possibilities that it could have done. Is that kind of the correct understanding, Arthur?
Oh, well, I'm not really sure what all this, what all this stuff exactly mean. I mean, each block, what does it exactly do? But I think in general, yeah, that makes sense. That it's just like a bunch of elements. You can, each is responsible for its own like function, and yeah, you collect a number of observations, and then you send this observation to an agent, and agents execute some policy, and then then you repeat it like in circular way.
Yeah.
And yeah, I think this structure is designed to be efficient. Like here, he mentions that you can play multiple, execute multiple play multiple games at the same time using multiple cores of your CPU, and training of the network is done on GPU. And yeah, this infrastructure allows efficiently execute all the program.
Yeah, so they've got a little bit of explanation of this diagram here. So it says, why are there multiple environments? So this is the bit down here where there's multiple environments. Instead of exploring a single environment, you generally want the driver to explore multiple copies of the environment in parallel, taking advantage of the power of all your CPU cores, keeping the training GPUs busy and providing less correlated trajectories to the training algorithm. Okay, so lots of environments, lots of stuff going on here, all sorts of batched updates going on up into that direction. Okay. And what is a trajectory? So this is the trajectories that are given to the observer. It is a concise representation of a transition from one time step to the next, or a sequence of consecutive transitions from time step n to time step n plus t. The trajectories collected by the driver are passed to the observer, which saves them in the replay buffer, and they're later sampled by the agent and used for training. Okay. Why do we need an observer? Can't the driver save the trajectories directly? Indeed, it could, but this would make the architecture less flexible. For example, what if you don't want to use a replay buffer? What if you want to use the trajectories for something else, like computing metrics? In fact, an observer is just any function that takes the trajectory as an argument. You can use an observer to save the trajectories to the replay buffer, or to save them to a TF record, or to compute metrics, or for anything else. Moreover, you can pass multiple observers to the driver, and it will broadcast the trajectories to all of them. Okay, so this is just making the architecture a little bit more subtle. Okay, so here, yeah, obviously we've kind of, yeah, I mean, they're saying here, okay, fine, we've described this architecture in quite a lot of detail, but actually the library is quite flexible, and you can, yeah, you can customize it a hell of a lot. And this particular approach to what they've done is not the only one that you can implement. And then they've got a DQ network. TF largely provides many networks in the TF agents networks package. And its subpackage, we will use the Q network class. Okay, so this is the Q network, which I guess we've already had a description of in the previous chapter. And it's got a quite detailed description about the activation functions and what the architecture of the Q network is, the filters, the convolutional neural networks, and so on and so forth. Okay, so that was the network architecture. Oops. And yeah, the fact that you can have multiple inputs, and then they've got a slight architecture of how to deal with the more than one input if you need to deal with that. And then how to create the DQN agent. So there's some code here to do that. Okay, and then creating the replay buffer and the corresponding observer. You know, quite detailed descriptions of the parameters of that, metrics, creating the collect driver. So what does this driver do? A driver is an object that explores an environment using given policy, collects experiences, and broadcasts them to some observers at each action step. The following things happen. The driver passes the current time step to the collect policy and uses this time step to choose an action and returns an action step object containing the action. The driver then passes the action to the environment, which returns the next time step. Finally, the driver creates a trajectory object to represent this transition and broadcasts it to all the observers. Okay, so the driver is kind of doing a little loop amongst all the different components. Okay, I'm not going to go through all of that. There's a data set. To sample a batch trajectories from the replay buffer, call is get next. This returns the batch process buffer info object. So this is all the stuff in the replay buffer. Okay. Yeah, I mean, I guess this is, really detailed. You probably need to execute this really to get an idea of exactly how this is working.
I agree.
Unfortunately, I don't have the time to do that.
If you're going to like implement your own environment, you will just go step by step through this and just do it.
Yeah.
Otherwise, it doesn't make much sense to study this code like in details. It's just straightforward implementation of what you need to achieve it.
Yeah. Yeah. And I think we might stop there.
He has
Sorry.
I haven't done now, but when we started this chapter, I was not getting any idea of what's going on. Then I went on to execute his code. So if you go on his repository and open the code he has given, all the descriptions is there initially. So I think that's a good idea to, execute it. And he goes into a step and then he explain a bit and then you go to a next stage. And then things start making sense, more sense.
Oh, okay. I wonder how quick it is. Because I mean, he's done like, like what's that? About 1 million, or is it 10 million steps?
It's slow. It's slow in a sense. I think first few steps were quick, and then afterwards, once you start adding the complexity, it takes quite a while because you have not only one loop, there is a set, so there are steps within a loop. So
and when the agents becomes better, every step takes longer because like if you play in a game, it would like play for longer.
That's correct. Yeah. So it's not going to be quick, but yeah, I think we should have started, or maybe we can next time we can start with the notebook directly, and then can relate.
I just executed the notebook from his repo, and it was it took quite some time, but I ran it on CPU. I ran it on Collab, but didn't use GPU. And I don't know, maybe it would be much faster when using GPU. But yeah, and I changed an agent from DQN to DDQN, and it doesn't seem to really do a good job. Yeah, it totally like broke, but DQN agent worked fine, at least for like it did 2 steps of something. Did you, Dinesh, get a good results?
I didn't use this week. It was, I think, last week or last when we started it. So I didn't. I'm just very beginning of the notebook, so it didn't go through. I think first 2 stages I managed to get it, but result-wise I don't remember. It was more of just executing to see, and I was just stuck. You know that poll, how the poll is going to go. So I just playing with that.
Oh, yeah, cool. Does the notebook actually produce a video at the end or anything like that to kind of show you what the final trained network did? Or because I haven't had a look.
I can just share my screen quickly and show you an animation of what.
Sure. Let me stop sharing, and I wonder if you can, or can I make you host?
I think I can share.
Yeah, sure. Okay, cool.
Okay, so this is this upper one is the last one we just did just finish, and you see it does just nonsense.
Yeah.
But the previous one was a bit better. Just you see it plays some couple of steps, and for some reason it just doesn't go for that like third one, and yeah, it seems like it really doesn't know what it's doing yet still.
Yeah.
Although it like do like 2 useful actions, but then it just doesn't even go the way it needs to go.
Yeah, it probably just needs longer training, I guess.
Yeah, because it was only 10,000 steps, and in book I think he had 1 million steps right there.
I think it might have been 10 million actually, but yeah.
Yeah, so you need to train for quite longer. But yeah, I probably restart it with GPU and see what can it do after a longer training.
Yeah.
It's fun, but you know, I think to really get it, you need to choose some interesting problem, and try to work on it.
Yeah. Yeah, I think so. I mean, if that paper is interesting, the one about the reinforcement learning for text generation, yeah, I might then be a lot more keener to really get into this stuff, because that's something that
I wonder what is the computational cost for running reinforcement learning on some reasonable size transformer for text generation. It should be like quite extensive.
Yeah, I mean, that's why you need a Google scale compute to do this stuff. It was interesting. I think, I don't know if it's true, but I remember reading when they sold DeepMind to Google that one of their main motivations was to get access to the compute because the compute was costing them so much. Yeah.
But
cool.
Hopefully it improves, and maybe it wouldn't be like move away from brute forcing and make some more sense of what it's doing by like really. I think just, you know, human learn much more efficiently compared to machines for now, and probably we can somehow bridge this gap. So it's interesting how it will develop.
It's interesting. While you were just talking there, I was just thinking this is actually a good candidate for those what was it called? You know, the transformers paper we looked at the other week, which was the one with the almost trillion parameters, switch transformers.
Yeah.
Because I mean, I wonder if you need this much training because the networks are not that big. that if the networks were bigger and more sparse, and then in theory, if the sample efficiency of that switch transformer fed into this guy as well, then in theory you might be able to train it a lot quicker by just having a much bigger network. But that's just a hypothesis because it worked really well in that particular situation.
And like having a specialized, like a bunch of specialized experts, like they did there.
Yeah, I mean, obviously all the experts are all trained, so they're not like hard. I mean, well, you know it better than I do, but yeah. But the main thing would be that because these are quite small networks, it's almost like they have to really generalize like a hell of a lot. To get the to get it to play really well. Whereas if the networks were much more deeper and bigger, then in some sense they might be overfitting a bit, but it would the learning would be quicker because they could keep a lot more of their knowledge because there's a lot more structure there for them to do that. But yeah, I mean, I'm guessing those guys have already tried it because this is such an obvious thing to try. But yeah, it would be interesting to play with that. But I wouldn't mind trying to implement that switch transformer model anyway, one of these days, unless Hugging Face does us a favor and does it for us.
Yeah, but I know this guy, Lucid Reigns. He has a lot of pieces of transformers implemented in his repos, and he has a mixture of expert thing, but I think it's just like particular brick of that. And yeah, it would be interesting to try this mixture of expert and see if it really brings some benefit on smaller scale, because probably we won't be able to like really train something giant. But
so did you guys get any feedback on that implementation you made for the other transformers architecture, or because you submitted it a couple of weeks ago, didn't you?
Yeah, about feedback, I'm not sure what feedback is supposed to be. I haven't heard anything yet. We like posted our results and everything, and but not much feedback for now. But maybe it will probably take some time, and maybe like for them to accept it or something. And also we applied for like weights and biases. So they give some prize money for training this, and if we like get those, we will probably use that prize money that's just 500, but like we could use it for training something else, and like re-implement another paper, and it's like maybe it will like have something out of it, but mostly it was just for me it was just learning experience. Because
no, I think well, I assume you learned a hell of a lot because I saw some of the code you'd done, and yeah, it was really sophisticated and really made a lot of heavy use of a lot of PyTorch features. So yeah, I wish I had the time to implement switch transformers because I would love to kind of implement that mixture of experts. I don't think it's that complex, but I just can't mentally imagine right now how I will do it, because the rest of it is just attention, various attention mechanisms. So but yeah, cool.
Yeah. Oh, about tomorrow's paper reading. So are we having a session tomorrow?
I was hoping to, although I've got to finish reading the paper tonight. So yeah, I mean, if you guys are okay, yeah, sure. I'm going to try and review that GEM paper.
Okay, that would be. Also, I read recently this DiBerta paper.
Okay.
It's one of the recent variants of BERT by Microsoft, and it's quite interesting. I think it would take not much time to like show what they tweaked to get better performance, and I could do that tomorrow.
Oh, that's fantastic. Yeah, let's do that. We'll do both of those. Would you be able to put on the Slack channel where what you were going to review, and I'll put mine, because we normally never announce them, and I don't know if anybody else is really genuinely interested, but I'm hoping, I mean, I should really start announcing these just in case there's somebody else who wants to attend, but they're just not really sure what time and what we're going to do.
Yeah, actually, about this DiBerta paper reading, I was attending a Kaggle session on Saturday evening, and they do this Quora question pair competition. I only attended it occasionally when I had time, not really doing this competition and everything. But also during that particular session, we were discussing another paper about SpanBERT, like another variant of BERT, which used changed the masking objective a bit to get better results. And during that session, we decided another guy should read Roberta paper, and I volunteered to read this DiBerta paper for review for that session too. And so I think there is some interest for reading papers, but I don't know what is the way to go about bringing more people to this group.
Yeah, I mean,
one thing you can do, Arshad. By the way, tomorrow mine is tentative. If I could join, I will.
No worries. I'll put the recording on anyway. Yeah.
Yeah, but I think I was just before coming to this class, I was listening to the conversation Joseph and Wencheng was having. They're starting a new class. So the best idea would be go to the journal Slack channel and announce there with the @channel. I'm like just doing a announcement there, like a big bang, inviting everybody with the @here or @channel. And I think then 6,000 people will listen, and then maybe people will respond back.
Yeah. I mean, it's just because I'm so busy at work, I can't always do every week. So I'm like, I don't want to let people on that this is going to be like really regular. But once I've got a little bit more time, I want to sort of put a little bit of like a history of what papers we've got in the future as well, so that people know, if they don't want to attend this particular one, or they might want to attend one slightly in the future, to create maybe a spreadsheet somewhere of papers that we will be reviewing and kind of rough dates. So, but yeah, no, that's a really good suggestion, Dinesh. I really need to do that because we don't promote it at all. There were more people attending. I think Wencheng convinced a few people when he was doing it, some colleagues.
Another problem is, I think it's the working hours in the US. So it's just start of the day. So that may be another issue. Because
I mean, we could do it sometime at the weekend, but unfortunately, the weekend is just so busy because Sundays they've got so many sessions going on. That we would end up being really quite.
One more suggestion about reading this paper, as Arto mentioned. I think in the Kaggle competition, which is around, I think it's on a Sunday. No, it's not a Sunday. It's actually Saturday, 2 to 4, 4 to 6. I think it's 6 o'clock on Saturdays, where they discuss the Quora question answers. So I think maybe you can join in there, and then
I'm going to try. I normally have my children, so I'll find it hard. But yeah, at least I'll try and see if I can listen to the recording at least the day after, because they are having some quite interesting discussions.
Okay, because it's like more practical, I think, and if you read some paper, you want to like get some results from it applied to your like Kaggle competition. It's really adds some value to the reading. Also, I was wondering if it would be nice to have some efficient way to summarize what we read, you know, really like to get this very brief summary of the methods and contributions for each paper, because you know, sometimes you can just forget what you have read at what time, and it would be useful to somehow like really
sure. I mean, well, I could create a little Notion folder, and for each
Actually,
paper, we can just create a little page, and
yeah,
each
so
person who does it can maybe put some notes on there.
actually, when this paper started, I created one Excel spreadsheet, and that's where exactly what I was doing, the paper name, link, and sort of like abstraction. I can share with you guys to see. Maybe we can refine that as well. So that's exactly what I was doing, because there were so many papers coming in the way. So I thought maybe I'll start making a list. But I think initially I created a list and then I didn't update it afterwards. Maybe that helps.
Yeah, sure. Share that, and
Yeah.
we'll see how we can fit it into the, you know, some kind of mechanism for doing this. Yeah, cool.
Yeah. Okay.
Okay, cool.
Okay, cool, guys. So
right.
yeah, hopefully I'll probably speak to you tomorrow. Yeah, I'll record the session anyway, Dinesh, if you can't make it. So and I'll share the recording afterwards.
That would be great. Thanks very much. Thank you.
Yeah, thanks, guys.
By the way, it's 4 o'clock, isn't it?
Yes, 4 o'clock. Yeah.
Okay. Okay. All right. I'll see. Thank you.
Thanks then. Right.